Neural networks can look intimidating when you first meet them. There are circles, arrows, layers, weights, biases, gradients, and activation functions. But the secret is that the whole topic is built from one small idea, repeated many times. A neuron takes numbers in, multiplies them by weights, adds a bias, applies a function, and sends a number out. That is it. In this tutorial, we will build from that simple idea toward exam-ready understanding. We will calculate tiny examples by hand, explain why neural networks are more powerful than one perceptron, and connect the theory to common practical terms like ReLU, softmax, dropout, and backpropagation. Treat this as a calm revision class. You do not need to know advanced calculus to follow the big picture. You need to understand what each part does, why it exists, and how to explain it clearly when the exam asks. Here is the roadmap for the hour. First, we start with the perceptron, because it is the basic building block of a neural network. Then we see why one perceptron is limited, and why connecting several perceptrons gives us more power. After that, we study architecture: input layer, hidden layers, output layer, depth, and width. Then comes activation functions. You must know step, sigmoid, tan, ReLU, and softmax at least at a conceptual level. Next, we study training: forward propagation, loss functions, backpropagation, gradients, optimizers, epochs, and batches. After training, we look at common problems such as overfitting and vanishing gradients, plus fixes such as dropout and regularization. Finally, we connect everything to classification regression, image recognition text models, and generative networks. If you can explain this roadmap in your own words, you are already thinking like an exam-ready AI student. A perceptron is the simplest artificial neuron. Imagine a small decision machine. It receives input features, such as hours studied and hours slept, or the number of times a word appears in a sentence. Each feature is multiplied by a weight. The results are added together, then a bias is added. This produces a score often called Z. The score is passed into an activation function. If we use a step function, the output is either 0 or 1. If we use a sigmoid function, the output is a number between 0 and 1, which can be interpreted like a probability. The important exam point is this: the perceptron is a linear model followed by an activation function. On its own, it can separate data with a straight boundary, but it cannot solve every pattern. Neural networks become powerful when many perceptrons are connected together. This formula is worth memorizing because almost everything in a basic neural network grows from it. The score Z equals W1 times X1 plus W2 times X2, and so on, plus the bias B. The X values are the input features. The W values are the weights. The bias is an extra adjustable number that shifts the threshold. Once we calculate Z, we apply an activation function. That activation could be step, sigmoid, tan, ReLU, or softmax depending on the layer and the task. In an exam, if you're given inputs and weights, do not panic. Multiply each input by its weight, add the products, add the bias, then apply the activation. That is forward calculation for one neuron. A full neural network is the same operation repeated across many neurons and many layers. Let us make the perceptron concrete with a student example. Suppose X1 is hours studied and X2 is hours slept. Our toy model says Z equals 2 times X1 plus 3 times X2 minus 18. Then we apply the step function. If Z is greater than or equal to 0, output 1, meaning pass. If Z is less than 0, output 0, meaning fail. This example is not meant to be a real education model. It is meant to make the mechanics visible. The weight 2 says study hours matter. The weight 3 says sleep hours matter even more in this toy formula. The negative bias minus 18 creates a threshold that the student must overcome. For exam questions, this kind of setup is common. You will usually be asked to substitute numbers and decide the output. Now calculate one prediction. The student studies 6 hours and sleeps 3 hours. Substitute the values into the formula. 2 times 6 is 12. 3 times 3 is 9. 12 plus 9 minus 18 equals 3. Now apply the step function. Since 3 is greater than or equal to 0, step of 3 is 1. So the model predicts pass. Notice how simple the calculation is when you slow down. The hard-looking notation is just multiplication and addition. In a written exam, show the score first, then show the activation result. If the question asks for interpretation, say the model predicts class 1, which we defined as pass. If the score had been negative, the step function would output 0, meaning fail. This little example is enough to understand the mechanics of a discrete perceptron. Weights and bias are not just symbols. They have meaning. A weight controls how strongly an input affects the output. A positive weight pushes the score upward when the input increases. A negative weight pushes the score downward when the input increases. A larger absolute weight means stronger influence. The bias shifts the decision threshold. Without a bias, the decision boundary is forced into a more restricted position. With a bias, the neuron has more flexibility. For exam wording, say, weights represent the importance and direction of input features, while the bias allows the neuron to shift its activation threshold. In the student example, sleep has weight 3 and study has weight 2, so sleep has a stronger positive effect in that toy model. The bias minus 18 means the student needs enough combined evidence before the model predicts pass. A single perceptron has an important limitation. It creates a linear decision boundary. In 2 dimensions, that means a straight line. If the data can be separated by one straight line, a perceptron can work. If the data needs a curve, a corner, or several conditions combined together, one perceptron is not enough. This is exactly why neural networks matter. A neural network combines multiple simple units, and the combination can form much more flexible boundaries. The chapter example uses alien sentiment. The aliens say words like awk and beep. The model counts how many times each word appears, then predicts whether the alien is happy or sad. The pattern is not simply more awk means happy or more beep means happy. Happiness appears when the words occur together in the right way. One line struggles, but 2 conditions can solve it. Here is the tiny alien dataset in exam-friendly form. If the sentence has only awk, the alien is sad. If it has only beep, the alien is also sad. But when both words appear together, such as awk beep, the alien is happy. More combined examples, like awk awk beep or awk beep beep, are also happy. This dataset teaches a deep idea using a silly story. Sometimes a class depends on a combination of features, not just one feature alone. In geometric terms, the happy points and sad points cannot be separated perfectly by one straight line. So instead of forcing one perceptron to do everything, we use hidden neurons. Each hidden neuron checks a simpler condition. The output neuron combines those conditions. That combination is the beginning of a neural network. Now look at the 2 hidden neurons. The first hidden neuron calculates 6 times the awk count plus 10 times the beep count minus 15, then applies step. The second hidden neuron calculates 10 times the awk count plus 6 times the beep count minus 15, then applies step. These are 2 separate perceptrons. You can imagine them as 2 tests. The final output neuron receives H1 and H2, adds them, subtracts 1.5, and applies step. This means the final output becomes 1 only when both hidden conditions are active. In plain English, the network says, classify the alien as happy only if both hidden tests agree. This is the core neural network idea. Simple units become powerful when their outputs become inputs to other units. Let us calculate the sentence awk beep. The count of awk is 1, and the count of beep is 1. For H1, calculate 6 times 1 plus 10 times 1 minus 15. That gives 1, and step of 1 is 1. For H2, calculate 10 times 1 plus 6 times 1 minus 15. That also gives 1, so H2 is 1. Now the output neuron calculates 1 plus 1 minus 1.5. That equals 0.5. Since 0.5 is greater than or equal to 0, the step function outputs 1. The prediction is happy. This example is excellent for exams because it shows forward propagation through a small network. First, compute hidden neurons. Then compute the output neuron. Always move from left to right during prediction. A neural network architecture describes how the neurons are organized. The input layer receives the original features. For the alien example, the input features are the awk count and the beep count. Hidden layers are layers between input and output. They learn intermediate patterns. In image recognition, early hidden layers might respond to edges, later layers might respond to shapes, and final layers might support class decisions. The output layer gives the final answer. Depth means the number of layers, especially hidden layers. Width means the number of neurons in a layer. A network with many hidden layers is called deep, which is where the phrase deep learning comes from. Do not make this too mysterious. Deep learning is neural networks with multiple hidden layers trained on data. Activation functions are essential because they introduce nonlinearity. The step function gives 0 or 1 and is useful for teaching perceptrons, but it is not normally used for gradient-based training. Sigmoid squashes any real number into a value between 0 and 1, so it is common for binary classification output. Tan squashes values between -1 and 1 and is centered around 0. ReLU, which means rectified linear unit, returns 0 for negative inputs and returns the input itself for positive inputs. It is very common in hidden layers. Softmax is used for multi-class classification. It converts several scores into probabilities that add up to 1. If the exam asks why activation functions are needed, the best short answer is, they allow neural networks to learn nonlinear patterns. ReLU is one of the easiest activation functions to understand. ReLU of z is max of 0 and z. If z is negative, the output is 0. If z is 0, the output is 0. If z is positive, the output is z itself. So ReLU of -5 is 0, ReLU of 0 is 0, and ReLU of 7 is 7. Why is ReLU popular? It is simple, fast, and helps reduce the vanishing gradient problem compared with sigmoid and tan in many hidden layer settings. In an exam, if you see a hidden layer with activation equals ReLU, that is normal. If you see a binary output layer, sigmoid is more likely. If you see a multi-class output layer, softmax is more likely. Matching activation to task is a common practical question. Forward propagation means computing the output of a network from inputs to prediction. In this tiny example, x1 is 1 and x2 is 2. First, calculate the hidden neuron. H equals ReLU of 2 times x1 plus 1 times x2 minus 3. Substitute the values. 2 plus 2 minus 3 equals 1. ReLU of 1 is 1, so H equals 1. Now calculate the output neuron. Y hat equals sigmoid of 3 times H minus 2. Since H is 1, that becomes sigmoid of 1, which is about 0.73. If this is binary classification and the threshold is 0.5, the model predicts class 1. This is the same process as the alien example. Calculate each layer in order until you reach the output. Once the model predicts, we need to measure how wrong it is. That measurement is called the loss function. If the true label is 1 and the model predicts 0.73, the model is close but not perfect. A simple loss example is squared error, 1 minus 0.73 squared. In real neural networks, the loss depends on the task. For regression, mean squared error is common because the model predicts a number. For binary classification, binary cross-entropy is common because the model predicts one of two classes. For multi-class classification, categorical cross-entropy is common because the model chooses among several classes. Training is basically the process of changing weights to make the loss smaller. If loss goes down, the model is learning the training data better. Backpropagation is the method that makes neural network training possible. After forward propagation, the model has a prediction. The loss function compares the prediction with the true answer. Backpropagation then moves backward from the output layer toward earlier layers and calculates gradients. A gradient tells us how the loss changes when a weight changes. If changing a weight upward increases the loss, the optimizer should move it downward. If changing it upward decreases the loss, the optimizer can move it upward. The full math uses partial derivatives and the chain rule, but for exam explanation, focus on the purpose. Backpropagation finds how responsible each weight is for the error. Then gradient descent or ADAM updates the weights. This repeats many times until the model improves. Gradient descent has one very important update rule. New weight equals old weight minus learning rate times gradient. The learning rate controls the size of the step. If it is too large, training may jump around and fail to settle. If it is too small, training may be painfully slow. In the example, the old weight is 0.8, the learning rate is 0.1, and the gradient is 0.5. Multiply 0.1 by 0.5 to get 0.05. Subtract that from 0.8 to get 0.75. So the new weight is 0.75. This small calculation is enough to understand the direction of training. The optimizer keeps taking steps that are intended to reduce the loss. Here are 5 training words that often appear in exams and tutorials. An epoch is one full pass through the training data. If the model trains for 10 epochs, it has seen the full training set 10 times. A batch is a smaller group of examples processed together before a weight update. The learning rate is the step size used when weights are updated. An optimizer is the algorithm that decides how to update weights using gradients. ADAM is a popular optimizer because it adapts learning behavior and often works well with little tuning. When you read Keira's code, these terms appear directly. Model.fit has epochs and batch size. Model.compile has optimizer and loss. Knowing the vocabulary helps you understand code without running it. XOR is a classic exam problem because it proves why one perceptron is limited. XOR outputs 1 when the two inputs are different, and 0 when the two inputs are the same. So 0, 0 gives 0, 0, 1 gives 1, 1, 0 gives 1, and 1, 1 gives 0. If you plot these 4 points, the positive examples are diagonal from each other. A single straight line cannot separate them from the negative examples. That means one perceptron cannot represent XOR perfectly. However, a small neural network with hidden neurons can solve it. The exam lesson is not just about XOR itself. The lesson is that hidden layers allow networks to represent nonlinear decision boundaries that a single linear model cannot. This small XOR network combines 2 simpler logical ideas. The first hidden neuron behaves like OR. It turns on when at least one input is 1. The second hidden neuron behaves like NAND. It turns on unless both inputs are 1. The output neuron combines those results. For x1 equals 1 and x2 equals 1, h1 becomes 1 because OR is true. h2 becomes 0 because NAND is false when both inputs are 1. The output then calculates step of 1 plus 0 minus 1.5, which is step of minus 0.5, giving 0. That matches XOR. For 0, 1 or 1, 0, both hidden neurons turn on, and the final output becomes 1. This is a beautiful example of neural networks combining simple classifiers into a more complex classifier. Overfitting is one of the most important training problems. A model overfits when it memorizes the training examples instead of learning a pattern that generalizes. The classic sign is a large gap between training performance and test performance. For example, if training accuracy is 98%, but test accuracy is 65%, the model probably overfit. Neural networks can overfit because they may contain many parameters. With enough parameters, a model can memorize noise, unusual examples, and accidental patterns in the training data. In an exam, define overfitting as good performance on training data, but poor performance on unseen data. Then mention that the goal of machine learning is not memorization. The goal is generalization to new examples. There are several ways to reduce overfitting. More data helps because the model sees more variety and has less chance to memorize a small set. A smaller model helps because fewer parameters mean less memorization power. Regularization adds a penalty for large weights, encouraging simpler solutions. Dropout randomly disables some neurons during training, which forces the network not to depend too heavily on one pathway. Early stopping means monitoring validation performance and stopping training before the model starts memorizing too much. You do not need to claim that one method always solves everything. A good exam answer says these methods help improve generalization. Dropout and regularization are especially associated with neural network training. The vanishing gradient problem happens when gradients become extremely small as they are passed backward through many layers. If gradients are tiny, early layers receive very weak learning signals, so they learn slowly or almost stop learning. Sigmoid and tan can contribute to this because their derivatives become very small in flat regions. ReLU often helps because, for positive values, its derivative does not shrink in the same way. This is one reason modern neural networks often use ReLU or ReLU-like activations in hidden layers. In an exam, explain the problem and the effect. Gradients vanish, early layers do not update effectively, and training deep networks becomes difficult. Then give common fixes. ReLU, better initialization, normalization, and improved architectures. Neural networks can be used for both classification and regression. Classification predicts a category. Binary classification has two classes, such as spam or not spam. A binary classifier often uses one output neuron with sigmoid activation and binary cross-entropy loss. Multi-class classification predicts one of several classes, such as handwritten digit 0 through 9. It often uses softmax output with one neuron per class and categorical cross-entropy loss. Regression predicts a continuous number, such as house price temperature or exam score. A regression neural network usually has one output neuron with no sigmoid or softmax, because the output should not be forced between 0 and 1. Its loss is often mean-squared error. Output layer and loss function are the key differences. This Keras example is a simple binary classifier. Sequential means we build the model layer by layer. The first dense layer has 8 neurons, uses ReLU, and expects 2 input features. The second dense layer has 4 ReLU neurons. The final dense layer has 1 neuron with sigmoid activation. That final sigmoid is the clue that this is binary classification. The compile step tells Keras how to train the model. Atom is the optimizer. Binary cross-entropy is the loss. Accuracy is the metric we want to report. In exam questions, you may be asked what each line means or why sigmoid is used at the end. The answer is that sigmoid produces a value between 0 and 1, suitable for a 2-class probability-style output. MNIST is a famous image recognition dataset of handwritten digits. Each image is 28 by 28 pixels. A basic fully connected neural network does not naturally receive a 2-dimensional image matrix, so the image is flattened into one long vector. 28 times 28 equals 784, so the input shape is 784. The output has 10 neurons because there are 10-digit classes, 0 through 9. A softmax activation converts the 10 output scores into probabilities that add up to 1. The predicted digit is the class with the highest probability. This example connects architecture to data shape. Always ask, how many input features are there and how many output classes are there? Regression neural networks are almost the same as classification neural networks, but the final layer changes. In this example, the input has 3 features, perhaps house size, bedrooms, and location score. Hidden layers use ReLU, just like many classification networks. The final layer has 1 neuron and no activation function. That is important. If we use sigmoid, the output would be squeezed between 0 and 1, which is not useful for predicting a house price or exam score. The compile step uses mean squared error because regression measures numeric distance between prediction and true value. In exam language, say, for regression, remove the final classification activation and use a regression loss such as mean squared error. Finally, know the major architecture names. A CNN, or convolutional neural network, is used mainly for images. It uses filters that slide over an image and detect local patterns such as edges, corners, and textures. An RNN, or recurrent neural network, is used for sequences because information from previous steps influences later steps. LSTM and GRU are improved recurrent architectures designed to remember information for longer. A GAN, or generative adversarial network, has 2 networks: a generator that creates fake data and a discriminator that tries to tell real from fake. Transfer learning means starting from a pre-trained model and adapting it to a new task. For most exams, you need high-level purpose and 1 example use case. Let us talk exam strategy. If asked what a neural network is, mention artificial neurons arranged in layers. If asked what a neuron does, say weighted sum, bias activation. If asked why activation functions are needed, say they introduce nonlinearity so the network can learn complex patterns. If asked what backpropagation is, say it calculates gradients of the loss with respect to weights and sends error information backward. If asked about overfitting, compare training and test performance. If asked classification versus regression, focus on output activation and loss function. Good exam answers are structured. Start with a definition, add 1 mechanism, then give a simple example. That style is clearer than writing every fact you remember. Here is the whole flow one more time. Input features enter the network. Each neuron calculates a weighted sum, adds a bias, and applies an activation function. Values pass forward through hidden layers. The output layer produces a prediction. The loss function compares the prediction with the true answer. Backpropagation calculates gradients by moving backward through the network. The optimizer updates weights using those gradients. This process repeats for many batches and many epochs. Over time, if training works, the loss decreases and performance improves. That is neural network learning in 1 paragraph. If you can explain this flow without looking, you are ready for most beginner AI exam questions on neural networks. That is your neural network exam crash course. Before your exam, rewatch 3 parts: the perceptron calculation, the XOR network, and the training loop with backpropagation. Those 3 ideas connect most of the chapter. Subscribe to Life of Geeks for more practical AI tutorials, and comment neural if you want the revision sheet and practice questions as a separate download. If this helped, share it with a classmate who is stuck on weights, bias, or activation functions. Keep studying in small pieces. Neural networks are not magic. They are repeated weighted sums, activations, loss, and weight updates. Once that clicks, the diagrams become much less scary.